All right, welcome back. So today we will talk about evaporation, and corresponding chemical potential difference. Okay, so in the last video we already talked about mu one minus mu two equals V 2 gamma divided by R. This is the scenario for this kind of curved surface, and this interface has a radius of curvature of R. Okay? Then, when we consider evaporation, this is liquid phase. And when the liquid evaporate and becomes a vapor phase, and this vapor has a radius of R, then you can simply derive this kind of equation from this equation. Okay, so mu R, mu infinite becomes V 2 gamma over R. Here, this infinite means radius of curvature equals infinite. So radius of curvature becomes infinite, meaning the curvature is 0, meaning flat. You can remember this. Okay? So basically, the chemical potential difference is this. And this R being the radius of this vapor. All right? It's very easy. All right. Now, we'll talk about how the vapor phase chemical potential change is derived. Okay, so when you think about the situation, then okay, so from the equation, dg equals mu 1 dn1 plus mu 2 dn2, and when it is equilibrium, this becomes 0, right? Then mu 1 dn1 equals minus mu 2 dn2. And since dn1 equals minus dn2, mu 1 equals to mu 2 when two phases are in equilibrium. All right? Then, so this is a condensed phase with radius of curvature equals to infinite. Okay? It should be equal to the vapor phase with infinite radius of curvature. Of course, because this kind of phase is in equilibrium, so of course you should be able to derive this, right? Same goes for this vapor phase. So mu C R equals to mu V R. Okay? Then this equation becomes mu V R minus mu V infinite radius of curvature equal to V2 gamma over R. Okay? Now, what about the condensed phase? We already learned that dg equals to minus SDT plus VdP. And since it is constant temperature, so dG equals to VdP. When we assume this is ideal gas, assuming ideal gas, then equal to VdP equal to RT over P dP. So dG equals to RT and P. Oh, sorry, D. Then mu C mu VR minus mu C infinite becomes RT ln P with R and P ln P with infinite. Okay, at standard state. This we already derive equal to mu V infinite. So mu V R minus equal to RT ln P. Wait, I made a mistake here. Sorry. It should be like this, right? ln PR P infinite equal to V2 gamma over R. Right? Now, so we can easily conclude that when R is smaller, then PR is bigger, right? When R is bigger, PR is smaller. This is vapor pressure of that particle, of that vapor, of this, meaning coalescence. So small ones will shrink. Big ones will keep growing. Very important point. I hope you remember the concept of coalescence. It is because of this. So this not only applies to liquid and vapor, it also applies to solidification. So when you have a critical nucleus, let me draw it for you. It looks like this. And this is critical radius. So this is a nuclei. Nuclei definition, meaning nucleus that can survive, meaning it can keep growing, okay? And this has a radius of R star, and this is G star. So basically, if you reach this R star, it will keep growing like this. If it doesn't, it will melt back down into the liquid. So here we are talking about solidification. We will deal with this in the later videos. But anyway, it's the same concept. So if it's big enough, then it will keep growing. If it's small, because vapor pressure is higher now. So it will shrink, right? It will go away, like these are atoms, right? And this is, you can say, is kind of like group of atoms, and of course they're gonna dissociate or melt back down in this case, or back in liquid and liquid and vapor phase, it will become liquid again. It will just go back in to the liquid, right? So obviously the smaller ones can't grow. Bigger ones will keep growing. Coalescence. All right. Thank you for watching.